Hi everyone, welcome back to PW English. Friends, as you know, we are continuing our UMEED NEET English series, and in this class, we are going to complete work, power, energy, right? So for all of you who are new to this batch is absolutely free. It is available on this YouTube channel, that is on PW English, as well as on PW app. So if you want these notes, please log into PW app. There you can find this batch along with all the notes, right? So what we do in these classes, we complete the chapter in one shot, all the theoretical concepts plus numericals, right? So without any delay, let's talk about work, power, energy. In today's class, we are going to start with, of course, work done. Then we are going to talk about work done by a constant force. Now I have not written the third point as work done by a variable force, but we are going to also talk about that as well, right? So we are going to talk about work done by a variable force as well. But remember, in NEET, so far they have been talking about some easy questions from work done by a constant force, but we are going to talk about variable force as well. Then we are going to talk about work done by graphical method, and the most important thing is we'll talk about conservative forces, non-conservative forces, their relation with potential energy. Further, we are going to discuss elastic potential energy, gravitational potential energy, and last topic is going to be work energy theorem along with power. So in short, we are going to do this chapter completely, right? So now let's start today's class and let's talk about what do we really mean by work done. See, the definition of work done is quite simple. Let's just say that we have got a body kept on a surface like this, and a force acts on it, and because of this force, this body gets displaces along straight line with, let's say, with some displacement s, right? So the work done will be written as the force. Now the force which is in the direction of the displacement. So let's just say that the displacement is x. Here the displacement is x, and when I said that, let's say that force is at any direction other than perpendicular, so this angle can be written as theta. So the component of force along the displacement is going to be F cos theta times displacement s. So this is the most easy definition. You can also define work after learning about internal work as well, right? So that is more technically, what we can say, technically sound definition of work done. But this is all good. We can just say that if a force is acting on a body in any direction other than perpendicular to the displacement, then we are going to say that work done by the force. So this is the thing. We are saying that this is work done. This is work done by F is going to be written as F cos theta into S. Also vector, in vector form we can write work done as F dot S, and when I say in vector form, I mean to say in dot product form we can rewrite the work done as F dot S. Please see that in this formula I'm assuming that force is a constant, and I have already said that the body is moving in a straight line, along a straight line, and it covers some displacement, which I have said that the displacement is S, right? Then we are going to talk about all the other things, that what if force is not constant, force is variable, what will happen after that, right? If force depends on position, if force depends on time, we are going to cover all of those things as well. But let's move step by step. So this is what work done is. Work is a scalar quantity. This is for sure. Work doesn't depends on direction. It is a scalar quantity, right? What else we can say? We can say that, okay, the SI unit of work done is going to be Newton meter. This is going to be the SI unit, or the another unit, that is the CGS unit, can be for Newton. We can say that it can be written as dyne, and this we can rewrite it as centimeter, right? So this is going to be nothing but 10 to the power minus 7 Newton meter. Hopefully this is all clear to all of you, right? Now after this, let's talk about some of the more things like what are the different types of work done. And when I say what are the different types of work done, let's just focus on this formula. When we are going to write it as Fs cos theta, when we are going to write it as Fs cos theta, let's write it under the work done by a constant force. Work done by a constant force is Fs cos theta. So the most simple thing, you have done these things in grade 9th as well. If theta is actually less than 90 degree, then in this case we say that work done is positive, right? If theta is equals to 90 degree, and this is actually an important thing because we are going to talk about many cases where angle is 90 degree, then we say that work done by the force is actually 0. This is an important case. And if theta is greater than 90 degree, that means the angle between the force vector and the displacement is, if it is obtuse, then we are going to say that the work done is negative, right? So as I have told you that these things you have done in grade 9, but we need to focus on this thing, which is actually when theta is equals to 90 degree, because there are going to be various places where we are going to see this case. For example, if we have got a pendulum, let's say that a bob has been attached from this string. This is a vertical line. Now we know that tension will act on the string something like this, right? And let's just say that the motion of the metallic bob at this point is something like this. So you can see that if this is the direction of motion, if this is the velocity, this is going to be the same direction of the displacement, the instantaneous velocity, right? So in this case, the angle that you can see is 90 degrees. So whenever this angle is going to be 90 degree, we are going to say that tension does no work, right? The work done by tension over here is going to be 0, and in any other case when you are going to see something like this, right? Now quickly let's move to some important point. The first point is related with the fact that we just saw the tension in the string of a simple pendulum is always perpendicular to the displacement. So work done by tension is 0. Please note this point, right? And it makes sense. After this, work is defined for interval or displacement. There is no term like instantaneous work, right? So because we have been talking about instantaneous velocity, instantaneous speed, instantaneous acceleration, but when we are going to talk about work, there is no term like instantaneous work or average work. Work is always defined for an interval or for a displacement, right? So whenever you're going to talk about work, it will be work. You don't need to have any confusion over here. For a particular displacement, work done by a force is independent of type of motion, right? So force does not depend, what we are trying to say over here is that force does not depend on the frame of reference, but displacement does, right? Displacement does depend upon the frame of reference. That's what we have done in, that we have studied in kinematics. For different frame of references, displacement can be different for a particular body. So if displacement is different, then we can say that work done also depends on the frame of reference, and work done can also be different, right? So that's what we have written over here. For a particular displacement, work done by a force is independent of type of motion. Sorry, this is about type of motion. No worries. So right now we are talking about type of motion. So whether the body is, if I'll explain it. Let's say if we have got a body over here, and this body is under some force, and because of this force the body covers 10 meter of displacement along the direction of force, right? So now whether this body is under retardation or whether it is accelerating, that is speeding up, it really doesn't matter. I mean, work done doesn't depends upon all of these things. That's what they have written. That's what we have got over here, that it is independent of type of motion. The point that I was talking about, it is over here. That is the third one, my friends. please first see the third point. That means a force is independent of reference frame. Its displacement depends on the frame of reference. So work done by a force is frame dependent. Therefore, work done by a force can be different in different frame of reference, right? So hopefully this point is also clear to all of you. What are the other 2 points? If a body is in dynamic equilibrium. Okay, so we are going to talk about this thing. But first, let's discuss what do you mean by dynamic equilibrium. See, equilibrium basically means that if you are saying a body is in equilibrium, no matter what type of equilibrium it is, the net force acting on a body will be 0. And if net force acting on a body is 0, we can conclude that net acceleration of that body or system is also 0. And if this is the case, 2 cases can arise. One is that the body is at rest. The next case is the body is moving in uniform motion. So if they are talking about dynamic equilibrium, this is the case they are referring to. That means we are talking about a system or a body which is under uniform motion, it is moving. So it is in dynamic equilibrium. The net force acting on it must be 0. So now let's come back to the point. If a body is in dynamic equilibrium under the action of certain forces, so we know that the net force acting on the system is going to be 0, right? But there can be different forces. The net sum is 0, the vector sum is 0. So the total work done on the body is 0, but work done by individual forces may not be 0. This is very important. What are we talking about over here? Again, I'll use a simple diagram. Let's suppose we have got a body something like this and it is moving under uniform motion with some velocity, let's say v. And after this, let's assume that we have got different forces over here. And for simplicity, let's just draw 2 forces. This is F1 equals to 10 Newton and this is F2 equals to 10 Newton. And we are assuming that the displacement of this body is, let's suppose it is 5 meters. So we want to calculate work done by these forces after 5 meter, right? So work done by F1 we can calculate it. So it is going to be 10 Newton times 5 meters times cos 180, as the angle between the displacement and the F1 is 180 degree. So this is going to be minus 50. Now the work done by F2 is 10 Newton times 5 meter times cos 0. So this is plus 50. So when we are going to talk about the total work done, we mean to say work done by all the forces, we are going to write work done by force 1 plus work done by force 2. It's going to be a scalar addition. It's going to be minus 50 and plus 50. That's it. So the net work done is 0 Newton meter, but individual forces may have work, right? So this is what it is. Please understand, and we are going to talk about all of these things again and again, when we are going to talk about conservation of linear momentum, right? Then also we are going to talk about that when you are talking about a system, individual forces, individual velocities, individual accelerations may change, but the system remains in uniform motion or the system remains at rest. All of those things. I'm just drawing an analogy from this topic to the conservation of momentum. For all those people who have studied conservation of linear momentum, they know what I'm talking about. If not, we'll again discuss that. So we have discussed the first point. We have also discussed the last one. The second point says when several forces act, work done by force for a particular displacement is independent of other forces. This is also, I mean, these questions are pretty basic. I mean, if you are lucky, NTA might come up with a question based on a theoretical concept, like a theoretical question, right? So the work done by F2 is independent of F1. Even if F1 didn't exist, the work done by F2 would remain same, right? Yes, the total work done on the system would differ. So this is the second point. When we are talking about several forces, work done by a single force is independent of all the other all the other forces, right? Second point is also done and dusted. Now let's move We have already discussed work done by a constant force. It is quite easy to find out the work done by a constant force, right? Let's talk about something like work done by a variable force. So force is a function of x, y, z. That means we are talking about work done by a variable force. All right, my friends, hopefully you are all now comfortable. It's been around like I think 15 minutes. Now I want you to watch this lecture completely, because the thing is, if you are comfortable with certain concepts, switch it to like 1.5x speed, 1.2.5x speed, but watch this whole lecture, because along with NLM, work power energy is one of the most basic chapter which will play a very important role in the concept building of physics, right? So this is very important. Now when we are talking about work done by a variable force, let's just assume that force is actually somewhat like this. I'm giving force in the vector form. Now you know the drill, J cap plus FZ K cap, right? Also, let's say that the body gets displaces from a point which has got coordinates x1 comma x2 comma x3, and it gets displaces to point B which has got coordinates, sorry, these coordinates are going to be x1 comma y1 comma z1, and these coordinates are going to be x2 comma y2 comma z2. Now we are going to talk about some other things as well, that if we are saying that force is variable, does force depends on path? We are going to talk about all of those things later on when we are going to start conservative forces. But for now, we are going to just say that in this case, let's assume that we are talking about work done for an infinitely small displacement. So F times, let's say I am talking about F times ds, a small vector, right? After this, I can rewrite this thing as dw is going to be written as f x dot dx plus f y dot dy plus f z dot dz. And if I want to find out the total work done, all I'll do is I'll integrate all of these things from x1 to x2, from y1 to y2, and from z1 to z2. That's it, right? And then you know how to integrate, how to use definite integration, and we are going to find out the total work done. For practice, we have got one question over here. You can see what force we have got written over here. It is just in x. You don't have to worry about. You just have to write it in x. Please pause the video, solve it by yourself, then unpause it and check. So force is given as 7 minus 2x plus 3x square. Mass of the body is 2 kg, and it moves and it displaces from x equals to 0 to x equals to 5. So the total work done is going to be the what we can say is f dot dx, right? Now you might write fx dot dx plus fy dot dy plus fz dot dz, but we don't have fy, we don't have fz. Even if they sometimes what they do is they'll confuse you. They'll write it something like this. See, they'll write it the body displaces from 0 comma 3 comma 2 to 5 comma 7 comma 10, right? But if there is no force acting along y direction and z direction, so we don't have to worry about those components, right? We will simply write f dot dx, and then the total work done will be the integration of this, and the limits are going to be from 0 to 5. let's just integrate it. Can I integrate it directly? The integration of 7 would be 7x, integration of minus 2x would be x square, integration of 3x square would be x cube. Now if you are having trouble over here, please watch basic mathematics lecture of mine. And now let's put the limit from 0 to 5. You don't have to worry about 0. Let's simply put 5. So 7 times 5 is 35 minus 25. Is that correct? Now we have got over here as 125. Hopefully everything is clear. So I think the correct answer is 135 joules. Hopefully you have got it. It was an easy one, but you can expect questions like these in NEET. Alright, so this was the first category, not the first category, second category. First category is absolutely easy, work done by a constant force. Now this is work done by a variable force, and under work done by a variable force, let's talk about another case when we have got something like work done by a variable force when force is given as a function of time. Now usually NTA doesn't ask questions from this particular topic in NEET, but as we all are expecting that NEET 2025 might be a little more difficult than the previous year, right? I mean, we all wish it happens. It's in our good. So when we are talking about something like this, what we'll say is, let's suppose, I'll give you an example. Let's say that we have got a block of mass 3 kg. I'll use some real numbers, 3 kg, and it is under a force, under an experience of force, which is given as F equals to, let's say, 2t square. Is that correct? And we have to find out the work. Now see, force is given as a function of time t, and we have to find out the work done by the force. Let's say work done from t equals to 0 to t equals to 2 seconds. Now, if everything is good, please do it by yourself. I think I have given each and every information. Do it by yourself. Check your answer. Pause the video, then unpause it, and then check your answer. Right. So we have got F. Now, please see what do we know till now. We know that work done. When we write small work done, we write it at something like work done equals to F dot ds. That's what we write, right? Now the problem is we have got force over here as a function of time, right? What else we know? We know that we can write force as mass times acceleration. That means 2t square equals to mass is 3 kg. Acceleration can be written as dv by dt. Hopefully everything is clear till here. Can I just rewrite dv as 2 by 3 t square into dt? Hopefully I can write something like this, right? And can I also integrate it? So if I'll integrate it over here. If I'll integrate it, I'll get something like v equals to, I've got over here as, this is going to become 2t cube, right? And similarly, I'll rewrite it as 2 by 9 t cube. This is what we are getting right now, an expression of velocity, right? Now, if you'll please see over here, I can again differentiate this equation. I can rewrite it as dw by dt, which later on we'll also write it as power times f dot ds by dt. Hopefully everything is clear, right? Now ds by dt is nothing but v. So I'll rewrite it as dw equals to f. Instead of f, I'm going to write it as 2t square, and instead of ds by dt, I'm going to write v, and v is coming out to be 2 by 9 t cube times, I'm going to rewrite this dt over here, and then I am going to again integrate it. I know it's a lengthy process, and we are going to integrate it from 0 to I think we have got time as 2, if I'm not wrong, right? So this is what we are going to do. All right. So this is going to be your answer for work done when force is given as a function of time t, right? Hopefully everything is clear. Please quickly have a look, then we'll move on from here. Now moving on after this, it's work done by graphical method, right? So you might come across some questions like these, where you have got x-axis, that means displacement along x-axis, force, and you have got a graph something like this, let's just say. So definitely it's a work done by a variable force, isn't it? So the area under this graph is going to be the work done, this area, and by the way, this is going to be considered as a positive area and positive work done. And this is basically work done is area under Fs curve, where S is the displacement, right? So now we can have another example. Something like this. So in this case, this is going to be negative work, and this is going to be positive work done. All right, so that's all. You don't have to worry about all of these things. These are quite simple. Let's have a look at one of the question. The question says, corresponding to the force displacement diagram shown in adjoining diagram, calculate the work done by the force in displacing the body from x equals to 1 centimeter to 5 centimeter. Now, only thing that you need to notice over here is that they are only asking about the work done from x equals to 1 to 5 centimeters. You don't have to find out the total work done. So x equals to 1 is over here and 5 is over here, right? Now all I can see is that this is 10. Now this length is 10, this is 1, so this is going to be 10 square units. This is again 1, this is 20, so this is going to be 20. And now from they are asking about from 1 to 5. For 3 to 4, again this is actually, this length is 20 and this length is 1, so this is going to be minus 20. So we can clearly see these things can be cancelled out, and from 4 to 5 again it is going to be 10. So the total answer is going to be 10 joules, and let me just see if this is in centimeter, right? This is in centimeter and this is in dyne, so the unit is going to be ergs. I mean, if I didn't tell you in the start, dyne times centimeter is erg, which is equals to 10 to the power minus 7 joules Newton meter, right? So pretty easy one, and that's all what you are going to see in questions under graphical approach. Now let's move to a certain different topics. Let's move to conservative forces, potential energy. First of all, let's talk about conservative forces. Now, when we are going to discuss this topic, I'll in the start I'll explain that there are basically two types of forces under this type of categorization, and these forces are basically conservative forces and non-conservative forces. Right now, the definition for conservative forces, now they are different points regarding conservative forces. They are different what we can say important points, notes, or you can say properties of conservative forces, but we are going to define it something like this, that work done by a conservative force or against a conservative force, or against a conservative force is, first of all, is path independent, is path independent, right? So this is the first thing that you need to understand, that when you are going to calculate work done by a conservative force or work done against a conservative force, it is not going to depend on the path. It is going to be only dependent on the initial position and final position, right? Also, we can say that, I'll write it in the next point. Also, again, same line, work done by or against a conservative force is recoverable, right? What do you mean by this? It means that when a force is going to do some work against a conservative force, we can actually recover that force. And how we are going to recover that force? We are going to now talk about a concept of potential energy. So that's why I have written these two things in the same line. We are going to talk about potential energy only when we are discussing about a conservative force, or only when there is a conservative force in the picture, right? We are never going to talk about potential energy when we are talking about a force which is not conservative. So these two things are what we can say are coupled. So work done by or against a conservative force is recoverable, and that's why we are talking about potential energy. What else we can say? We can say that extension to the first point, that these are path independent. This means that it only depends on final and initial position, So if you are going to we are going to discuss types of conservative forces like gravitational, elastic, potential energy, and so on. But if you want to have an example, we can quickly take one example. Like, let's suppose this is a ground, right? And we want to actually displace an object of mass m from ground to this height h, right? Now there can be various ways of doing this. You might have seen again this thing in grade 9th also. There can be various ways like this. Let's suppose one of the path is something like this, the another path is somewhat like this, and one of the path is directly in upward direction. So in all of these three paths, the total work done by the external force is going to be just mg, which is the weight, times displacement, which is h. So this is, by the way, this is work done by the force. I'm not saying work done by gravitational force. It would be minus mgh, right? It does not depend upon the path along which the body has moved. It only depends on the initial position and the final position, right? So that's all you need to actually understand about conservative forces. And obviously we are going to look for some more important points over here. Now the thing is, when we are well, this point is actually related with potential energy, so I'm going to come to that. But before coming to those important points, let's focus more on the concept of potential energy. Now see, I told you that we have got a body kept over here. Let's take an example of gravitational force, and the mass of the body is m. We know that gravitational force acts on this body as mg. We want to elevate this body up to a height of h, right? So if we want to do that, And when we say that we want to actually move this body up to this height of h, we want to displace it under zero acceleration. We don't want its the velocity should increase, right? So we are going to actually apply exactly the same force, that is the external force is going to be exactly equals to mg that's right, right? And if we are going to talk about work done by external force, that is going to be mg times h, and if you are going to talk about work done by gravitational force, that's going to be minus mg times h. Now these two things are quite easy to understand, but when we are going to talk about that recoverable thing, that the work done by or against a conservative force. So this is the conservative force that we are talking about. Gravitational force is a conservative force. Right? Work done by or against a conservative force is recoverable. So please understand that that's what we say, that we assume that this is the reference line. This is the reference line, and we assume that gravitational potential energy of this line is actually zero. Let's just assume that gravitational potential energy is zero. So the gravitational potential energy at this point will be the amount of work done that the external force has done, because the external force has done the work on the body, so this will be stored on the body. So the potential energy at this point, let's say I'm calling this point as point A, and I've not used point B, so I'm going to take this as point B. So the potential energy at point B will be mgh, right? That's it. We are going to also write one more formula for potential energy. So potential energy is mgh. If you are going to closely see, the change in potential energy is actually mgh minus 0, and that is equals to the work done by external force. Also, change in potential energy is equals to the negative times of the work done by conservative force. Now these things are very important to remember and easy to understand, right? This is very important because when you are going to talk about work energy theorem, these things should come organically to you, that okay, this is the conservative force. Work done by the conservative force will be written as negative times of change in potential energy. Now whatever that potential energy, if it is gravitational potential energy, use the formula of mgh. If it is elastic potential energy, use the formula of half kx square, whatever that is, right? So this is what you must remember. Now the other thing is, please understand that work done by conservative force can be written as work done. Now sometimes we rewrite this thing as del u also, right? So if this is the case, please look here. We know that work done can be written as dw equals to conservative force times ds or dr, whatever you want to call it, right? F dot dr, and you can use the vector signs also if you want. Now I have said that okay, the work done is actually equals to change in negative times of change in potential energy, so I'll write it as du. Right now I'm talking all the changes that I'm talking about right now is infinitely small. So this means that force can be written as negative times of du by dr. Another important thing. And it is going to, after this, it is again going to open many more concepts for you. That force can be written as, this is sometimes known as negative times of potential gradient, right? This is known as potential, simply known as potential, right? Or potential energy. So du by dr can be called as potential gradient. So force is equals to the negative times of potential gradient. What do we mean by this? You are going to come across this again in electrostatics in grade 12th. There you are going to talk about electrostatics force and electrostatics potential energy or potential gradient, right? Same thing. Now please understand what do we mean by this. This is the conservative force, this is negative times of du by dr. Now I can write force as, force along x-axis, force along y-axis, basically the vector sum of all of these things. And also dr can be written as x I cap, y j cap, and z k cap. Now, after this, you need to understand that we can rewrite this equation as a partial derivative equation. Where we are going to actually rewrite it as f equals to negative times of del u by del x plus del u by del y plus del u by del z. What do you mean by partial differentiation? Hopefully you know this concept, but for all of those students who don't know, partial derivative basically means when you are going to actually differentiate potential energy, and when you are trying to differentiate potential energy with respect to x, so you might be having terms of y and terms of z. Treat them as constant. It is as easy as that, right? So when you are differentiating with respect to x, treat y and z to be constant. When you are differentiating u with respect to y, treat x and z to be constant, and same thing for z also, right? Now, although we are not going to have many more questions over there, because this is more important than that is to understand the equation over here, why we have got a negative sign, what do you mean by potential gradient, and to explain that I'm going to use an example of class 12th electrostatics. Now I know many of you might not have yet been there. Well, for all of those students who are in drop year, you know what I am going to talk about, but for all of those students who are still in grade 11th, you might not have done electrostatics till now, but believe me, the concept is going to be very easy to understand, because it only deals with the basic concepts. And that is, let's take an example. Let's take a system of two charges. Now please understand, there's going to be nothing that you didn't know. Let's suppose we have got two charges separated by a distance. This dotted line is nothing but to denote distance. It is, let's say it is separated by a distance of r. We have got a charge plus q1. I've got a charge of plus q2. Is that correct? Everyone knows like charges repel. That's why I was saying that there's going to be no concept that you didn't know earlier. Like charges repel, everyone knows. This means that this Q1 applies some repulsive force on Q2. You might not know what that force is. By the way, that force is known as electrostatics force, but let's just write it as force applied on Q2, by Q1. That's it. And this is force applied on Q1 due to Q2. Can I also write force applied on Q1 due to Q2 is negative times of Q2 due to Q1? Now, please understand, I'm not talking about a new concept, and this is the beauty about physics. This is the easy thing with physics is, you have done all of these things in Newton laws of motion. You have read that like every other force in universe, every other force exists in action reaction pair, right? So these are nothing but action reaction pair. This is nothing but Newton's third law. what is the magnitude of that forces? We are going to talk about that in electric charges and fields, in electrostatics. That we are not going to do in today's class. But all of these things are in your course, right? Now please understand, if I want to decrease this separation, if I want to decrease the separation, understand what I'll have to do. First of all, let's say that this particular charge is fixed right now. We have fixed its position. And now I'm saying I want to actually decrease their separation. So you're going to say, okay, in that case, you will actually have to apply an external force in this direction. So to do this, and this is the electrostatics force, which is the conservative force. I could have used another examples as well. I could have used gravitational force, but I believe that you can actually understand about all of these concepts with this example in great detail. This is the electrostatics force. It is a conservative force. Why is that? Because when you are going to actually apply an external force on this charge, and when you are going to actually decrease the separation, the amount of work done that this external force has done against this conservative force will be stored in the potential energy of this system. I'll repeat myself. When you are going to, when I say you, I mean to say the external force. When the external force is getting applied on this Q2, it does some work. It does some work on this system, which increases the potential energy of this system. Or what you can also see is the conservative force is in the direction where the potential decreases. Is that clear? Please understand, if I am decreasing the separation, the potential energy of the system is increasing, right? You can have another example like a spring. Let's just consider that this is a spring. We have got a fixed wall. I'm decreasing the separation. If you are assuming that it is a spring, potential energy is increasing, right? If this spring is going to go in this direction up until its natural length, potential energy is going to decrease. Is that correct? Similar thing will happen over here as well. When this particle will go in this direction, well, you can say that how will it will go when let's suppose that I'm not applying this external force no more, right? So it will start to move in this direction because of this force. So the potential energy is decreasing. So in this direction, the potential energy decreases. And in this direction, the conservative force acts. So that is what we have written over here, that potential, the conservative force is equals to the negative times of potential gradient. Negative stands for the decrease and potential gradient. Now you know what we are talking about, right? So I mean, if you know all of these concepts in work power energy only, then we can say that the physics will be a little bit more simpler in future chapters. Is that all clear? Now we can play with all of these things. We can you can also use this concept in the conservation of linear momentum also, right? Now if we are going to talk about, if I'll say that this is not fixed, let's say that this is not fixed, right? You can use this example over there as well. I'm not going to start that topic right now, because right now my focus is on potential energy. So after this, please understand, what we are going to do over here is, now we can look for some notes, right? And those notes are, case 1, on increasing x, if potential energy increases, then force is in negative direction, that is attraction force. Let's read the case 2 as well, and then I'll again go back to my example. Case 2 says, on increasing x, if potential energy decreases, force is in positive direction, that is repulsion force, right? So for now, let's just not worry about this positive and negative direction. Let's see whether they are talking about attractive forces or repulsive forces. So let's come back. So if you increase x, potential energy decreases. So these are the repulsive forces, like charges repel each other. If in the same type of problem, we are going to say that we have got a positive charge and we have got a negative charge. So they are, now we are going to have an attractive forces over here. And if you are going to now again decrease, see what they were asking about. Now if you are going to actually increase x, potential energy will increase. Is that clear? Just a second. Quickly see both the points. Quickly see both the points. Hopefully everything is clear now, right? So if you are going to increase x, potential energy is going to increase, that's for sure. If you are going to actually, now in this case, if you are going to increase x, the system wants to come close, the charges wants to come close. If you are going to increase the x, the potential energy is going to increase. If you didn't get it, pause the video, think about it, write down this example on your notebook, you will get it, right? So these are the two cases. Now let's talk about equilibrium and types of equilibrium. Now here I'm not going to talk about the dynamic and static equilibrium. Here, first of all, whenever you are going to say that a body is in equilibrium, a body or a system, right? So there can be two cases. See, instead of writing like this, I'll just explain. Either we can say that the system is in equilibrium, or we can say a body is in equilibrium. Is that correct? Whatever we try to say, equilibrium basically means the net force acting on the body. This implies that the net force acting on the body is zero. Along with this, we also mean, when we say equilibrium, we also mean the net torque acting on the body is zero. But right now we are not discussing this. Right now we are not talking about torque, but you must know it. And when we say net force acting on the body is zero, this further implies that the net force, the sum of all the forces along x-axis is zero, sum of all the forces along y-axis is zero, sum of all the forces along z-axis is zero. There can be individual forces, but when you are going to do the vector sum of all the forces, it must come out to be zero. Same thing with the torque as well. That means anti-clockwise and clockwise. Some of those things is also zero. When you are talking about system, whatever is inside the system, all the particles, every body, each and everything must follow these two things. Is that correct? So it is very important whether they are talking about a body is in equilibrium or a system is in equilibrium. If a body is in equilibrium, same thing. If a system is in equilibrium, same thing, but for the entire system, right? Now what is system? Hopefully you know that. After this, we are going to talk about, if this is all clear, then now what are the types of equilibrium? Now to just explain it in a very simple way, and this is a type of example that you are going to see in different books and different what we can say notes as well. The example is something like this. Let's suppose we have got a case something like this. Let's suppose we have got three types of body over here. We have got one body like this. We have got one body like this. Let's say this is body A. This is body B. And this is body C. Right? And if I'll actually do one thing. Yeah, it's all right. Now, if I'll displace this body, what do you mean by displace this body? That if I'll apply an external force on this body, something like this. If I'll apply an external force on this body, what will happen is, it will actually it will because due to some acceleration, force will create some acceleration, body will move. And again, this is a type of an analogy. I'm going to write mathematically what do we really mean by the three types of equilibrium. But when you are going to apply a force on this, the body will get displaced and a component of weight will act in this direction. A component of a force of weight will act in this direction, which will actually try to bring this body again to this position. And again, well, when it will reach this point, it will again some gain kinetic energy and it will again go back to this point. And then again that weight will act. That weight will act all along, but again at a particular point, its kinetic energy will become zero and it will keep doing SHM, keep doing a harmony, an oscillatory motion, something like this. Having said that there is no loss of energy. Is that correct? So this type of an equilibrium, why this is an equilibrium by the way, because at this particular point weight is acting downward, that is mg, normal reaction by the ground is n, which is equals to mg, and there were no forces till now, till we applied any other force, right? So normal reaction equals to mg, so net force is 0. So this is an equilibrium. The next case is, what type of an equilibrium is this? This is a stable equilibrium. Why? So the first type of equilibrium is actually known as a stable equilibrium. And the reason is, the definition is that when you are going to apply, when you are going to actually displace the body from the stable equilibrium, a restoring force will act on the body, which will try to restore. That's why we call it as restoring force, which will try to restore the original position of that body. That is known as stable equilibrium. Now, similar thing, if you are going to do it over here, if you are going to apply an external force, the body will never be able to reach back to its original equilibrium position. This type of equilibrium position might be called as unstable. Similarly, if you are going to actually apply a force over here, the body will roll down, it will reach somewhere over here, and there is no difference between this equilibrium position and this equilibrium position. The third one is known as neutral. So you have got stable, you have got unstable, the B was neutral, and the third one is unstable. But we have got better definitions for this. We have got better, what we can say, we have got better mathematical way to put all of these things. For stable equilibrium, the first thing that we are going to say is definitely that the net force acting on the body will be 0. Well, this is for any type of equilibrium. So from this, we can also imply that du by dx is 0, or whatever you want to call it as du by dr also, right? So du by dr is 0. This is absolutely true. The special thing about the equilibrium, the stable equilibrium is, if you are going to look at this example, this was the stable equilibrium, and at this point, the potential energy of this particular body was minimum. Please understand, if you are going to talk about, like, I mean, this is the case for the conservative force, which is acting over here is gravitational force, right? So I'm going to talk about gravitational potential energy. So when this body reaches to this height, the gravitational potential energy increases. Then this body, when it reaches to this height, again the gravitational potential energy increases. From here till here, x is increasing, and gravitational potential energy here, it is actually it is positive. It decreases, it becomes 0. And then if again I actually increase the x, again it becomes positive, right? So the thing is, the potential energy for stable equilibrium, this is the important thing, that the potential energy in stable equilibrium is minimum. This is the thing. And if you want to rewrite this thing in a mathematical way, that will be d2u by dr square will be greater than 0. That is the rate at which the potential gradient changes should be positive. All right. So, we can have an example over here. Like this is the graph between potential energy and x, right? So the places where the gradient is 0, so those places are this point P, this is point Q, this is point R. At these places, we can say du by dx is 0, du by dx is 0, and du by dx is 0. Well, after s also we have got similar situation. Du by dx is 0. Now what I was talking about, the slope of potential gradient. See, du by dx is already the slope of the graph of potential energy and x. Now if I am going to talk about slope of du by dx, that is what we are talking about, that is d2 u by dx square. This is gradient of potential gradient. What is it? So at point P1, if we are going to closely see at point P1, d2 u by dx square is actually less than 0. The gradient is negative, right? You can see the gradient is negative. At this point, du d2u by dx square is actually greater than 0. So first it was negative. I'm so sorry. My bad. I should write it as du by dx, right? My bad. Du by dx is greater than 0. Now see, potential gradient is negative, potential gradient is 0, potential gradient is positive. So first it was 0, then it became, first it was negative, then it became 0, then it became positive. This means that the rate of change of potential gradient is positive. That is why we say that d2 u by dx square is positive. Is it all good, my dear friends? Right? So this is the case for stable equilibrium. So the point P is a case for stable equilibrium. You could have said to me that we don't have to worry about it, as we can see that point P is the minimum potential energy. So P is the stable equilibrium, Q is the unstable equilibrium, and S is going to be the stable, neutral. So this is unstable. Why unstable equilibrium? Now you can rewrite all of those things. Unstable because here we have got potential energy as maximum, right? And at this point you can say that there is no change in potential energy, right? Change in potential energy is 0. So that's all you need to actually understand. If with all of these information, your concepts are going to be pretty good for clearing NEET. Now we can come back to certain questions, although I have not written for unstable, but you can now write it by yourself. This is the first question that we have got over here, and please again pause the video, do it by yourself and then check. The question says the potential energy between two atoms in a molecule is given by U equals to A over x to the power 12 minus B over x to the power, I think it's 6, x to the power 6. where A and B are some positive constant and X is the distance between the atoms, the system is in stable equilibrium. All right. So the system will be in stable equilibrium. So for it to be in stable equilibrium, the first thing that we must do is we must differentiate the x as the u with respect to x, and we must equate it to 0. So with this we are going to actually get, my friends, that would be minus 12 a by x to the power 13 minus, it would get plus 6 b by x to the power 7. Hopefully that is all good, right? So from here, this is one of the case, and then the next case is going to be, from here we can get one answer. From the next case is going to be that d2u by dx square must be greater than 0. So if this should be greater than 0, we can imply that minus 12 a x to the power 13 plus 6 b x to the power 7 should be greater than, okay, should be greater than 0. So this is going to be minus 12a x divided by 13 should be greater than minus 6b x to the power 7, right? And when you are going to actually cancel these things, please don't forget to change the sign of the inequality. If you're not going to do that, bad luck for you. So this is going to be around 6, this is going to be 2, right? This is actually, this is one of the case, and I think we are going to get the stable equilibrium answer for the first one only. That is the thing. You don't have to actually worry about. This will be in stable equilibrium only. That's what they are saying, right? So we are going to get our answer from there only. So this is nothing but, this is actually a by 3. This is actually a by 3, and I've got over here is, sorry, this is actually 2a by x to the power of 6, and this is actually b, right? And if I'm going to actually rewrite this thing, so this is going to be 2a by b equals to x to the power of 6. So x would be 2a by b whole to the power of 1 by 6. Please see, please see. So I think option C is absolutely correct, but you check it. Let me know in the comment section if you have any doubt. Right. So now let's move to another one, and I'll give you one question in homework. So you have got a similar type of problem. You have to find whether it is in stable, unstable, or in neutral equilibrium. So do this one in homework. Write down the answer in the comment section, and this is from slide number 23. So write down in the comment section. Now let's move to another type of of potential energy, which is elastic potential energy. In Newton's laws of motion, we have discussed it, that let's suppose we have got a spring attached with this wall, and let's say this is the natural length. So this point is natural length. That means the spring is neither compressed nor elongated, right? Now after this, if we are going to say that we have applied an external force in this direction, we have applied an external force in this direction. So in this particular case, spring force will act in this direction, opposite to that of external force, and after a certain displacement, work, we are going to say that work is done by external force against the conservative force, that is this spring force. So again the concept of potential energy will come into place, and we are going to say if we want to find out the work done will be the integral of f dot dx, let's say from natural length to some elongation x. Now we know that force is nothing but kx. I'm talking about the external force, not the spring force. Definitely the spring force is actually minus kx. So this is going to, when you are going to integrate it, it's not a big deal. We can simply write it as half kx square. So this is work done by the external force. Right? And this is going to be the change in potential energy. Now let's quickly come to work energy theorem, because everything is same, right? So when you have already talked about like gravitational potential energy, conservative forces, non-conservative forces, force is equals to minus du by dx, everything will remain same for elastic potential energy as well. This is actually now very important, and the to all of those students who are watching this video, I'm going to say that I'm going to explain a little a type of a trick, a type of a way to solve the problems regarding work energy theorem, right? And that is of mine. So please watch this entire topic. When we are talking about work energy theorem, what it is all about. Let's say we have got a body kept on a surface, could be smooth, could be rough, and the net force acting on this body is, let's say, F, and because of this net force, the body is moving with certain acceleration A and has got mass M, right? So what are the different things that we can write? Well, we can definitely write that force can be written as mass times acceleration. Why we are trying to write something like this? Because we also know that the work done is written as F dot ds. Is that correct? So if force is written as m into A, force can be further written as m times v times dv by dx, if you remember this thing from the kinematics. Acceleration can be written as velocity times dv by dx, right? So after writing this thing, this means that f dot dx, well, please don't mind, I've written dx over here and written ds over here. I'll just change it and I'll write dx, right? Same thing. So I can write f times dx equals to mv times dv. That's it. This is the work done by the net force. Work done by net force, all the forces, mind you, right? This is what dw is. So after this we can write dw can be written as mv. Well, this is not work done by net force, I would be wrong to say, and I'll explain it to you why. This is dw equals to mv times dv. Now let's integrate it, and now let's write it as w. Now this thing can be written as work done by all the forces, right? Equals to, if I'm going to integrate it, and let's suppose that at this particular point the body was moving with some initial velocity u, and after a certain point it moves with with some final velocity v. So we want to integrate it from u to v. This is v with we need to integrate v with respect to v. It would be half mv square. You know what we are trying to do. So it is going to be half m v square minus half m u square. This is the most simple thing that you can see, but see how many concepts is going to actually open now. This is what I was talking about. This thing is work done by all the forces. And this is change in kinetic energy. This is what work energy theorem is, that work done by all the forces, work done by the net force will be equals to the change in kinetic energy. We are going to expand a little bit. What do you really mean by the net work done? So the net work done basically means, or work done by all the forces means, work done by conservative force, work done by non-conservative force. We really didn't focus much on non-conservative forces, but what non-conservative forces are, which are not conservative, like friction force, right? If you are going to find out the work done by friction or against friction force, those things we can't recover that work done, right? We can't talk about potential energy due to friction. All of those forces are friction force. They depends upon the path, plus work done by what we can say external force, plus work done by pseudo force. All of these things is equals to change in kinetic energy. This is again the work energy theorem. Now again we know that work done by conservative force is actually equals to negative times of change in potential energy. Is that correct? So I can substitute it. So I'm going to write work done by non-conservative forces plus work done by external forces plus work done by pseudo forces will be equals to change in kinetic energy plus change in potential energy. Why I'm writing it as potential energy? You know it, right? Here I've written negative times of change in potential energy. So again, this is also a case for work energy theorem. Now, most of the time what is going to happen is, most of the time these pseudo forces are going to be 0, or even if they are not equals to 0, this is what you are going to write, right? So this is known as conservation. Well, what do you mean by conservation of mechanical energy? I'll explain it. So if work done by non-conservative force is equals to work done by external force is equals to work done by pseudo force is equals to 0, then we are going to imply that change in kinetic energy is equals to negative times of change in potential energy. Simply write it as U, which means that change in kinetic energy is final kinetic energy. I'm going to bring down that final potential energy equals to initial kinetic energy plus initial potential energy. This is what conservation of mechanical energy means. COME, conservation of mechanical energy. Have a look, then we'll solve some problems on this. Hopefully everything is clear till here, right? Now what was the trick that I was talking about? Let's have a look. Now you know how to actually write the work energy theorem. Let's suppose we are writing something like, we are having a problem something like this. Let's start with an easy one. A body is moving with a velocity of 20 meter per second, has mass of 1 kg. Till here the surface was smooth. After this the surface is rough. Right? Alright. Let's suppose you want to find out when the particle will come at rest by work energy theorem. Is that correct? So what we are going to now say in this case is, we are going to use the work energy theorem, and theoretically the work energy theorem should be written something like work done by conservative force, we don't have a conservative force over here. Work done by non-conservative force, well, we do have a non-conservative force, plus work done by external force, we don't have an external force over here. Work done by pseudo force, we don't have anything. We only have got non-conservative force. That's it. Equals to change in kinetic energy, right? So what is work done by non-conservative force? So let's suppose that the this mu is given as is 0.1. So the friction force will be mu mg, mu times normal reaction, that means 0.1 times 1 times 10, that means 1 Newton. Is that correct? So friction force will act in this direction and displacement is happening in forward direction. So I'm going to write friction force, that is 1 Newton times displacement times cos 180 equals to, I'm going to find out the change in potential energy, change in kinetic energy. The final kinetic energy will become 0 minus half m into v square. Easy thing. That's how you're going to write the equation according to the work energy theorem. Now, what's my method? My method is quite simple. Now, let's suppose again you have got like two types of things. Let's suppose now I'm saying that we have got a similar type of a diagram. Now we have got one more element and that is spring. We have got one more element, that is spring, and body is moving with a certain velocity of 20 meter per second, 1 kg. Till this point the surface is smooth and this is rough with a coefficient of 0.1 and the K is actually equals to 50 Newton per meter. You have to find out what is the compression, what is the maximum compression of this spring. Again, you can do the same thing. You're going to write work done. Do we have a conservative force? Yes, we do have a conservative force, right? We have got a non-conservative force also over there. So I'm going to write work done by non-conservative force equals to change in kinetic energy plus change in potential energy. How this potential energy came into place? Because now we have got spring force also. Everything settled, right? But writing this equation like this, what was the trick that I was talking about? My trick is about, it's like, let's suppose that you have got a pocket money. Let's just consider that you have got a pocket money. This is what the trick that I was talking about. And you have got a pocket money of, this was of 200 rupees. Why 200 rupees? Because here the kinetic energy at this point, the initial kinetic energy is 200 joules. Is that correct? Right? Half m into v square. Square of 20 is 400. 400 divided by 2 is 200. So let's suppose you have got a pocket money of 200 rupees. Now you are going to market. You're going to market. So what you will do, you will spend. Now what are the expenses over here? You will spend something and whatever the money that will be left, that will be your saving. These are the two concepts, my dear friends. One is you have got a pocket money, you have got an amount. The reason I'm talking about pocket money is that you might not be earning right now. So you have got a pocket money, you're going to a market, you're spending, and then whatever is left, whatever money you have got left after all the expenses, that is your saving. Now please see here. This is the pocket money. What are the expenses I'm talking about? So 200 joules. equals to the expenses is actually work done in friction. You're going to say, but sir, just now here you written have work done by friction. What I was trying to do is I always, when I write work done by friction, I have written cos 180 over here, something like this, right? So this is what my trick is. You just write 200 joules. Okay, what is work done by friction? Just quickly find out what is the work done by friction, right? Plus, what are your savings? Your saving is just half kx square. That's it, my dear friends. That's it, right? And this is x is also the work done by friction in which you are going to put it, right? That is what my trick is, and we are going to solve some problems on this trick, right? Hopefully you have got it. Now let's move to some questions. So now let's move to one question. Do it by yourself, do it by the trick, right? It's really not a trick, it's just a way of quick thinking instead of just writing all the forces, and it's another way of thinking, right? Doesn't matter if you want to do it by yourself, do it. The question says, in the figure shown, all forces are smooth and force constant of spring is 10 Newton per meter. Block of mass 2 kg is not attached with the spring. Alright, so it is not attached with the spring. The spring is compressed by 2 meter and then released. So it is compressed by 2 meters and then released. So when it is going to be released, the block is going to move away, right? So if it is compressed, surely it has got potential energy. So that potential energy is written as half kx square. And equals to what are the expenses? The expenses is that it will gain some kinetic, it will gain some, finally some potential energy over there, and then it will stop. So I'm going to write mgh. Let's say it reaches up to this height, and this is, let's say this is h, right? So in this case, I'm going to find out first what h is. So this is going to be h will be equals to half k. So k is going to be equals to 10 Newton per meter times x square, right? And x was also actually 2, and divided by g, and divided by mass, that is 2. So I think everything is being cut. So this is coming out to be 1, right? So if this is 1, then we know that basically tan 30, sorry, not tan, of course, sin 30 would be equals to h upon, let's say this is d. So h would be equals to, we have to find out what d is. So from here, d would be equals to h upon sin 30, that is 2 times 1, that is 2 meters. So your 2 meter is the answer. Hopefully you have got it, right? Moving to the next one. Do it by yourself. Again, the block shown in figure is released from rest. Find out its speed of the block when the spring is compressed by 1 meter. So this is natural length. It is actually, right now it is elongated, right? So right now it is elongated. So the total potential energy is half k. By the way, my friends, have they not put what k is? I don't think so. K is missing. So if k is missing, let's just assume that the spring constant is k only, right? This is what we have assumed. So half, in this case, we are going to write half k x square, and this is going to be 4, equals to, now see how I do it. This is all my cash, equals to half mv square, the kinetic energy, the speed of the block when the spring is compressed by 1 meter. So half m v square, that this is what I need to find out, plus half, it will also have some potential energy because now it is compressed, plus half k x square, right? I can cancel out this thing, and this is going to be 3k equals to 2v square. So v would be actually equals to root of 3k by 2 if k is k what we have chosen, right? Hopefully you have got it. Done. Now, another question for all of you. Force acts on a 3-gram particle in such a way that position of the particle as function of time t is given as x equals to this, where x is in the work done in the, so this is just about the work done. I mean, it's not of a big deal. It's the force acts on the particle in such a way that the position of the particle is function of time t. X is given as 3t minus 4t square plus 3t cube, and they are talking about the work done. So I think you can do it quickly. Solve this question in homework. This is from slide number 31. Homework. All right. Let's do some questions from work energy theorem. Let's see what do we have over here. Find out the distance traveled by the block as shown in the diagram if the initial speed of the block is v and mu is the friction coefficient between the surface of the block and the ground. Well, what to worry about this one in this case, right? Well, it has got certain kinetic energy. It is half m v square. Is that correct? And equals to, when if the initial speed is v, we have to find out, and mu is the coefficient, we have to find out the displacement. You don't have to worry about it. It would be mu mg into x. That's it. Mass can be cancelled out. X will be v square by 2 mu g. This is going to be our answer. Quickly check, then we'll move on. Moving to the next one. Okay. By the way, this one, okay, this is, I have given you in homework. This one is velocity time graph for a particle of mass 2 kg moving in a straight line is as shown in work done by the forces. Okay, so work done by all the forces is going to be equals to change in kinetic energy. That's all you will have to do. So half mass is 2 kg and this is actually square of 20 minus 0. And by the way, this is actually initial is 20. So this is going to be 0 minus square of 20. So this is going to be minus 400 joules. This is going to be the answer. And that's how you are going to actually do the previous problem also. The question that I've given in homework. Okay, just differentiate it, find out the velocity, change in velocity and do it. Now, how to do problem like this? A body of mass m is slowly hauled up the hill. So this body m is slowly hauled up. That means slowly pulled up the hill. Now, what do you mean by slowly? When they specifically they mention this word, it means that there is no change in kinetic energy. It is not speeding up. This is actually an important concept. By a force with which at each point was directed along a tangent to the trajectory. So according to this, I am also going to tell you what happens according to this. Find out the work done performed by this force if the height of the hill is h and the length. All right. Hopefully you can see the diagram clearly. At this particular point, mg will act downwards, of course. I mean, at this particular point, let's say the angle that the tangent makes. So let's suppose this is the tangent. So the angle that this tangent makes is theta. This is actually theta. Let's say it is a small angle. All right. So at this particular point, I'll actually draw the diagram over here. Let's just suppose that this is a small angle theta. Let me write this thing as dh, this thing as dl, and the forces that I'll draw over here is, obviously I've got an mg. I'll write this as normal reaction, mg cos theta. Over here I've got mg sin theta, and also one more force, that is friction force. So I'll rewrite this thing as, this is going to be mg cos theta, and when they said that it is always directed along the tangent, it means that this does no work, right? So work done by normal reaction is 0. Also, I've got mg sin theta over here at this particular point, plus I've got mu mg cos theta, that is friction force, mu mg cos theta. Is that correct? Now, if this body gets displaces by, let's suppose this length is dx, or whatever you want to call it, let's call it as ds, right? So work done by mg would be negative times of work done, or why work done by mg? Let's find out the work done. The total work done will be at this small point, it would be minus mg sin theta times ds plus mu mg cos theta times ds. Hopefully this is all good. Instead of finding work done by mg and work done by friction force separately, I have just written it like this, right? You can do it by that also. Now please see over here that sin theta is nothing but perpendicular dh upon ds. So dh can be written as sin theta ds. So you have got sin theta ds. Instead of sin theta ds, let's write minus mg dh, plus similarly I'll write cos theta equals to base dl by hypotenuse, that is ds. So dl will be written as ds cos theta. So this is going to be again mu mg. Instead of ds cos theta, I'm going to just write dl. And by the way, this was the small work done for this small theta. So if you want to find out the total work done, just integrate this dh. So integrating dh would be h. So this is going to be mgh plus mgl. That's how you're going to find it out. Done? So hopefully this is all good. Moving on to the next one. Moving on to the next question. What is it about? A system of wedge and block is as shown in figure is released with the spring in its natural length. All the surfaces are friction lengths. Find out the maximum elongation in the spring. What will be the maximum elongation? I think this is all easy. So I want you to solve it. Only one force is acting in downward direction, that is mg sin theta. And one force is acting in upward direction, that is kx, right? So now you know that the maximum elongation will be the case when kx and mg sin theta will become same. So you can find out what x is going to be, right? So it is quite easy. Let's not worry about this one. Let's move to the next one. A body of mass m is released from a height h of a smooth inclined plane that is shown in the figure. Okay, this is the case. The following can be true about the velocity of the block, knowing that the wedge is fixed. V is highest when it just touches the spring. V is highest when it just compresses the spring. But okay. So the question is actually about this. It is quite again easy. What are the different forces we have got over here? We have got an mg sin theta acting downward. Right? Because of this mg sin theta, it will actually speed up, and it will speed up till which point, that is what the question is. Now usually what students do in this one is they actually select option A. The reason is they say that okay, this will actually mg sin theta will be there till it reaches at this point, and after this a spring force will start to act in the opposite direction, something like this. As soon as the block touches the spring and it tries to compress it, something like this happens. Mg sin theta is acting in this direction and Kx, that is the spring force, is acting in this direction. But this is a wrong approach and actually incorrect concept. The reason is when the block will first strike the spring, still at that point mg sin theta will be greater than Kx. Are you getting it? I mean, it will strike it down, but it will not suddenly, mg sin theta will not get smaller than Kx. It will compress it for some length that will vary according to the question, but it will compress it up to a certain length, and as it compresses, Kx will start to increase. At a particular point they will become same. After that, when Kx will further increase, then after the velocity will starts to decrease. Is that correct? So the correct answer is going to be V is highest when it compresses the spring by some amount, right? So B option is absolutely correct. Hopefully you have got it, right? Now after this we have got one more concept left, that is of power. Now I have actually tried to explain more questions on work, power, energy when we will do circular motion. So what I have done is I have actually broken down the chapters into portions. Like in Newton laws of motion we didn't completed circular motion for a simple fact that I wanted us to complete work energy theorem. Then when we are going to talk about circular motion, we are going to use work energy theorem, we are going to use Newton laws of motion, and then we are going to talk about that chapter as well. So in a way we have actually separated these chapters. Now when we are talking about power, power is nothing but rate at which work has been done. So if you write it as dW by dt, you are talking about instantaneous power. Or when you are talking about average power, you are talking about del W by del T. Right? dW by dt can be further written as, we know that dW can be written as F times ds by dt. So this thing can be written as F times velocity. So these are some of the important things about power you need to know. Other than that, it's nothing. There are no concepts which are going to be difficult over here. The SI unit is going to be watt, and it's also a scalar quantity. And keep your focus on this formula because in many questions you might use F times V, right? So now I think with this I'll give you one question in homework. A ball of mass 1 kg is dropped from a tower. Find the power of gravitational force. Now it is quite easy. If it is dropped, initial velocity is 0. Find out the velocity after 2 seconds. So 2 seconds would be just 20 meter per second. Is that correct? Right? And force is going, so the power will be actually equals to force. Force is actually mg. So that is 1 times 10 and 10 times 20. So this is going to be 200 watt. So that's it. So in a way we have completed each and every topic. The most important topics of today's class were conservative forces, non-conservative forces, work energy theorem, right? So hopefully you enjoyed this class. If you did, please share your review, share your feedback in the comment section. I'll come up with circular motion next week. So please complete Newton laws of motion, then work, power, energy, and then circular motion. So a major portion of mechanics will be covered, right? So I'll see you soon. Thank you so much. Bye bye. Take care.